So we've got a series of excellent plenaries, and this will be followed by a series of talks that have emerged from the road mapping process, and much more of that a little bit later. But first, to open our conference, I'd like to introduce Baroness Brown, who plays a key role on the Committee on Climate Change, chairing the Adaptation Committee. And I think we've all come to understand the importance of adaptation in recent weeks. Baroness Brown is also chair of the Henry Royce Institute Governing Board. So without further ado, I'm delighted to introduce Professor Dame Julia King, Baroness Brown of Cambridge. Julia.
Thank you very much, Neil, and good morning, everybody, and great to see so many of you on this video conference. I'm just going to give you a quick kind of context in terms of reminding you about the scale of the energy transition that we face. So could I have the next slide, please? And then the next slide, please. So just a bit of context then. We passed the Climate Change Act 11.5 years ago, committing us to reduce emissions by 80% from a 1990 baseline. And then almost exactly a year ago, Parliament updated that and said, agreed that we should commit to reaching net zero emissions by 2050. So if we have the next slide, please. It was actually pretty challenging to get to 80%. The key things we need are lots of energy efficiency, lots of electrification, things like electrification of our vehicles, lots of growth in our zero carbon power generation, obviously, to provide that electrification. But even with all of these measures, we end up with quite significant remaining in emissions in a number of sectors. And those that are particularly relevant, I think, to this discussion on the energy transition are those sectors of industry, aviation, heavy transport, and heating our buildings. So if I can have the next slide, please. Getting from 80 to 100% doesn't sound like that big an extra challenge. I'm a great one for saying the 80% solution, meaning we're nearly there. But actually, when you look at the kind of difference in pace of reduction in emissions, it actually is quite a challenge over the next 30 years. So the red dotted line is the rough kind of trajectory from getting where we are now, which is the black line coming down in emissions. The red line was getting to 80%. The green line is getting to 100% or net zero. So it's quite a scale up in what we need to do. Can we have the next slide, please? And if we look at what we need to do to get there, well, we need to really get the last emissions out of our electricity system, and we quite likely need some hydrogen to do that. Buildings is an area of real challenge. All sorts of new technology is going to be needed, new insulation materials, and also probably some hydrogen there too. Transport, we may well need some hydrogen for our heavy vehicles. Industry, probably going to need some hydrogen there, but also a bigger drive for electrification, and also changing some of our industrial processes like steel making. In terms of waste, we're going to need to see much more recycling and a real focus on the circular economy. Important things to do in shipping, in aviation, etc. But hydrogen actually becomes a very important part of the picture. Could I have the next slide, please? So just to really kind of imprint on us the scale of the changes we need to make. We've got to, in the next 30 years, we've got to somewhere between doubling and quadrupling the size of our electricity system, probably nearer the doubling, but in some of the scenarios, we get to 4 times as big electricity generation system as we have today. We have to increase the generation from offshore wind by almost an order of magnitude. We have just under 10 gigawatts operational today. We need to get up probably to somewhere between 75 and 100 gigawatts. That's a huge growth in that industry. We've got to start pretty much from scratch a hydrogen industry and grow it to provide the amount of energy that's just about equivalent to our electricity system today. we've got to start from scratch a carbon capture and storage industry. We have some 30 million buildings that need to be converted to low carbon heat. So if we did that on a kind of steady pace, that's 1 million buildings a year over the next 30 years. We've probably got about 250,000 really low carbon cars around in the UK. We have to change over the entire car fleet, and changes in afforestation, changes in the way we use land, changes in our diets. So that is a huge amount of change. We've done things of that magnitude historically, we just haven't done all of those things at the same time, or all of so many things of that magnitude at the same time before, I think. So this really is a big challenge, and it brings with it some fantastic and huge materials challenges. So the little diagram at the bottom just shows the increase in size of wind turbine blades, or of wind turbines, and hence of wind turbine blades. So, you know, people are now making composite blades some 120 to 130 meters long. We've seen almost an order of magnitude increase in the power of wind turbines over a period of individual turbines over a period of less than 20 years, in fact, enabled by applying advanced materials to this challenge. So if I can have the next slide, please. I want to end on the note of saying materials and developments in materials are absolutely key to unlocking this transition and enabling it to occur at speed. So there's going to need to be lots more work on hydrogen. And that beautiful diagram you said, the beautiful micrograph you saw earlier was from Bristol University and was one of these beautiful nanostructures that we may be able to use for storing hydrogen. Buildings are an area of particular challenge where we're going to need lots of low carbon materials, insulation, fuel cells, heat pumps, new ways of heating and cooling them, and absolutely enormous area of challenge where we really do need lots of innovation. And of course also where building controls will be very important. So again, lots more electronics that will need to be low energy. And indeed, electronics will be something that truly enables energy efficiency, just as lightweighting and new lightweight materials. So ultra efficient electronics, ultra efficient communications are all a key part of this transition. Decarbonising industry, it's going to mean using hydrogen, but things like low carbon steelmaking, something that the team at Sheffield and others in the Royce Institute are working on. Very crucially, we're going to really need to see a move to the circular economy and looking at waste, but also looking at resource availability. Some of these key elements that we're going to be using in all of these electric vehicles and things, we need to be making sure that we are recycling them continuously and not continually digging up the planet. Lots of materials challenges for transport, and lots of materials challenges in delivering this transformation and growth of our power system, whether that's cleverer composite turbine blades, more efficient photovoltaics. So just one example of the innovation is the work at Cambridge University on coatings for photovoltaics using very, very clever physics to enhance the efficiency of the photovoltaics. And I hope we're going to hear about more of those sorts of exciting developments today. But also, of course, better energy storage, because we're going to need to store the energy from the variable generation. We're going to be able to need to store the hydrogen that we're going to produce. So all of these are absolutely fundamental to delivering this transition. And all of these come from the materials research that people are doing. So it's going to be really exciting to hear today about some of the pathways that are going to be using developments in materials that are really going to enable this energy transition. So final slide, please. Just to say thank you very much for listening, and I'm really looking forward to hearing about the road mapping and the presentations to come. Thank you very much indeed.
Julia, thank you very, very much indeed for that excellent introduction and for setting us up for the conference to come. So next slide, please. And the next slide, please. Thank you. Next slide. Yeah. So in 2019, the UK, as Julia has just been discussing, the UK put into law a target of net zero emissions by 2050. So what this conference is looking at is essentially 4 key areas. But I just want to look at this particular slide here, and the areas that we've chosen to look at, we'll look at residential, energy to supply, transport, and mainly businesses. And they comprise most of the issue that we have to address. I also want to note that we did not address, for example, nuclear energy, wind energy, or batteries, partly because nuclear and wind are mature technologies, and batteries are supported by the Faraday Institute. So next slide, please. So we looked at the future of materials and photovoltaic systems, low carbon methods of hydrogen generation, decarbonisation of heating and cooling, and low loss electronics. And the cartoon on the right shows you where the energy and the electricity goes. Next slide, please. So we looked at 4 topics, and the first topic was the future of materials and photovoltaic systems. Now, photovoltaics energy potential is over 100 times greater than the UK's electricity usage per year. But currently, photovoltaic supplies only around about 4% of the UK demand. So to meet net zero, we need to increase the number of solar cells by at least an order of magnitude. We need to generate over 50% more power per panel. We need to utilize light from more of the solar spectrum. We need to be able to work in much lower light levels, for example, indoors, and we need to be able to enable carbon neutral buildings. And finally, we need to power electric vehicles and aerospace applications. Next slide, please. The second topic we looked at was low carbon methods of hydrogen generation. Now, fuel cells can generate electricity with absolutely no greenhouse gas emissions. However, they rely upon hydrogen. Currently, around about 95% of the world's hydrogen is generated by steam reforming of natural gas and other fossil fuels at very high temperatures. So can new materials enable green hydrogen production scalable to the terawatt level, or more efficient hydrogen production? And can the devices be much longer lasting for the hydrogen production? And finally, can we encourage the uptake of hydrogen through alternative chemical carriers, such as ammonia? Next slide, please. The third topic we looked at was decarbonisation of heating and cooling. Now, 37% of the UK's greenhouse gas emissions arise due to heating and cooling. Caloric materials and thermoelectric materials can create carbon-free heating and cooling alternatives. But how do we improve the performance, for example, of thermoelectric materials? And can thermoelectrics compete ever on efficiency with other technologies? How do we improve the performance of caloric materials? And we'll hear a lot more about that later. And can calorics replace current gas-based heating and cooling technologies? Next slide, please. Finally, we looked at low-loss electronics. And 40% of, as we saw in the cartoon right at the beginning, 40% of primary energy consumption is electricity, and 30% of all electrical energy passes through power electronics. And that's going to reach 80% in the next decade. 3 to 5% of global electricity is used by computing, and that's predicted to increase by up to 21% by 2030, or 8,000 terawatt hours. So there's a huge, huge opportunity here, but what materials will enable more efficient power electronics? What materials can reduce losses in CMOS? And what materials will enable beyond CMOS technology? And finally, what is the technology readiness of these opportunities? Next slide, please. So we undertook a road mapping process, and the idea was conceived at around September 2019. And we collaborated with the IOP, the Institute of Physics, in October 2019, and we engaged the Institute for Manufacturing to carry out our road mapping process. At the same time, the IOP carried out a questionnaire, and we had 272 responses from a community survey between February and March of 2020. We have a series of online workshops between March and June 2020 to do the road mapping, and today we are launching online the key findings of that. But it's not over yet, because we need to do community refinement. So we're going to come back to you and ask you more questions and ask for your views about the results so far. And then we're going to publish the roadmaps in September 2020. Next slide, please. So we've been busy, and so have you. The roadmap contributors come from around about 170 participants in 26 workshops from 48 organizations. And I must say, I do thank all of you who participated in this. It's made it's been a great event to see how this is coming together. Today, we've got well over 500 delegates or who've signed up at least for today's launch. Next slide, please. So there were key findings common to all of the topics that we looked at. The need for infrastructure to transfer technology from lab to prototype devices, national facilities for device metrology and degradation testing, national coordination of industrial and academic research programs, targeted investment from UKRI to unleash the potential of the research, and legislation for the uptake and implementation of low carbon technology. Research materials should be resource abundant and scalable and recyclable. And finally, of course, people, training, PhD programs, PDRA support, and so forth. Next slide, please. So what's the impact of all of this? Well, the impact for the UK will be that it will help us meet our 2050 net zero target, creating new jobs and filling the skills gap, and finally, providing energy security for the UK going forward. Next slide, please. And now I'm going to hand over to my colleague, Manish Chawala, who's going to introduce the plenary session. Thank you very much. Over to you, Manish.
Now it's my pleasure to chair the plenary session that includes 4 world-leading experts. The primary aim of this session is to put the road mapping exercise in context of the broader energy field. Next slide, please. So before starting the plenary session, a little housekeeping. If we have time, we will have a question and answer session after the plenary talks. Please submit your questions during the talks via the question box. You may address your question to a specific plenary speaker or to all of them. Finally, could I kindly request that the plenary speakers complete their talks within 5 minutes. For now, it's my pleasure to introduce the first plenary speaker, Professor Claire Gray from the Chemistry Department at the University of Cambridge. Claire is a fellow of the Royal Society. She's a world-leading scientist in the field of batteries, having made seminal contributions in fundamental understanding of how batteries work using operando characterization, as well as many other discoveries in the field. So on to you, Claire. You've already got your webcam and microphone on, so please start.
Thank you. It's delighted to be there as the first speaker. Next slide, please. So what I'd like to do in my 5 minutes is just to pitch the fact that in order to make batteries applicable for the 2050 agenda, we have a lot of work to do. Next slide. So I think it's very important to remind people, first of all, why this is important. Everybody knows about the electrification of transport and the issues associated with the cost, for example, in cars. But the bigger challenge is, how do you think about finding batteries for example, the lorries that will enable transportation of goods around the UK? And then the even larger challenge is how we use batteries for the grid. So we're not going to enable the use of the photovoltaics and the wind that Julia has talked about in her previous thing if we don't think about how we do storage. And we're in the position now where batteries are doing a good job for short-term frequency regulation, but if we're really going to make them batteries to have impact of those sort of hydro systems, then we really have to scale up massively and reduce cost. Next slide. So it's another important thing to recognize that we really are very close to the theoretical limits of the materials. And so we need, within the context of the 2050 agenda, to come up with radically new approaches if we're going to make impact. So the price of the battery has come back down by more than a factor of 10 since it was first invented, by new materials and some engineering. And the next improvements are largely going to be due to the scale, for example, of all the gigafactories that are being built around the world. But we're pretty much at the theoretical limit in terms of how much we can get from the materials that we're using in today's batteries. So we've improved from about a factor of 3 from the original lithium cobalt oxide systems to the NMCs and other systems like that. But if we're going to make changes, we're going to have to come up with radically new chemistries and get them to work in a cost-effective way and deal with the safety consequences. And this little laptop, sorry, the little Samsung Galaxy phone is just there to remind everybody that just even trying to get 10% or 5% extra energy density has resulted in safety consequences. Next slide, please. Then the other critical issue is sustainability and storage. So lithium and cobalt and nickel are all critical resources. And as electric vehicles are pushing away from lower cobalt to higher nickel contents, it isn't just the cobalt that is the issue, it's the nickel. And the resources are coming from parts of the world, such as DRC in terms of the cobalt. But in the lithium, there are lithium brines being mined in Chile and Bolivia, where they're some of the most driest parts of the world, and they have environmental consequences, the people who live there and the animals that are in that habitat. And so increasingly, we've got to change the way that we think about batteries, moving them to being inherently recyclable so they're easier to pull apart, and that's built into the whole design of the battery system. Next slide, please. So there are some simple ways to reduce cost. We can make cheaper materials. We can think about making bigger batteries, but there's tremendous materials challenges in how you design a system so that you can move the ions and the electrons in and get the same rate and deal with the fact that the batteries expand and contract throughout their lifestyle. And so there's a lot of fundamental science that needs to be done to determine or improve the way we control materials in non-equilibrium environments. And I'll touch on that in a minute. And then we have to do this in a much more efficient way. So the current battery assembly process in itself produces a lot of carbon during its manufacturing process. Next slide, please. So just to reflect on a few things, the first thing that we need to do is to stop batteries from degrading. And so the Faraday Institution is formed to inspire the lead the UK's battery activity, particularly in the automotive sector, and I lead the degradation project. And I think this is one of the critical ones because improving the lifetime of a battery is inherently important in terms of the sustainability and also the cost issues. Next slide, please. But it's not just about improving today's generation batteries. For the 2050 agenda, we have to come up with radically new systems. There are simpler ones like trying to get materials of higher energy density to work, such as silicon, which in principle offers you, just based on the silicon, a 10-fold improvement in volumetric and gravimetric capacity. Turns out that's less than a pack level, but nonetheless has to be achieved. A lot of challenges with it. Just to remind people, when you cycle a battery between charge and discharge, it operates outside its thermodynamic window. So the electrolyte and decompose as you're cycling to form this thing called the SEI. This continues all the time, and so that's a problem and a degradation issue that has to be solved. Next slide, please. We then need to think about, are there other systems beyond the traditional lithium ion? We could think about sodium ion batteries, good for the grid because they're cheaper. Magnesium batteries in principle give us highest energy density, but as we all know, as material chemists or physicists and chemists, it's much harder to move magnesium 2+ ions through solids. Turns out it's also harder to get them out of solution because they're well solvated. So a big challenge, but worth looking at in the 2050 agenda. Next slide, please. And then we need to think about radically different systems. So we have the lithium sulfur systems, where problems of the dissolving the sulfides are an issue, but we need new ceramics to address that issue. The lithium air space is sort of the highest energy density possible, has the same theoretical energy density as as gasoline, both practically and theoretically, but lots of challenges because it brings us the challenge of a fuel cell and the battery together. Next slide. But progress is being made. This is just one little illustration of work by myself and Peter Bruce and others using redox mediators to help shuttle ions backwards and forwards, going closer to making this a viable technology. The next slide, please. Then thinking about solid state batteries for improving ceramics, again, thinking about from a fundamental level, how do you move ions across all these multiple interfaces? How do you deal with volume expansions and contractions? Next slide, I'm almost there, Manish. And then when you start really thinking outside the box, you need to move away from a confined system where the box is your electrochemical cell defines how much energy density you have. And if you have a redox flow battery, you can flow in as much liquid as you want to do the reversible chemistry. And it starts to make you link together a battery and fuel cell. And while these systems are not yet any cheaper than lithium-ion batteries, they give you potential scalability. And I think they're very much part of the future and should be part of any research agenda, particularly for batteries for the grid. And we should do that in the context of new fundamental science. And so the next slide just gives you a couple of those. I would argue we need to understand how the processes from the atom level through the pack level work. We need to understand how you control materials under harsh and non-equilibrium conditions, and to understand and to control how we design interfacial processes. Next slide, please. And we need to do this via in situ metrologies to look at what's happening as the materials are operating. Next slide, please. And design new materials to make this happen. So this is just an example of some high rate materials for fast charging. And I just want to end with the final slide, I hope, by saying there's a lot of space out there for different chemistries and new science, but it's a really challenging process where we need to understand from the bottom up how to control metastable processes and non-equilibrium systems. So thank you very much for listening.
Thank you, Claire, very much. It's my pleasure now to introduce our next plenary speaker, Professor Jenny Nelson from the Physics Department in Imperial College London. She's the head of Climate Change Mitigation Team at the Grantham Institute, and her current research focuses on molecular semiconductor materials and their applications to organic solar cells. She became a fellow of the Royal Society of Chemistry in 2016 and was a recipient of the Faraday Medal from the IOP in 2016. So on to you, Jenny. Thank you.
Thank you, Manish, and thank you, Neil and others for the organization. Can I have the next slide? And the next. So, next please as well. So we've been, next please. Thank you. So we've seen this has already been mentioned, the photovoltaic field market has been growing extraordinarily rapidly at a rate of more than 30% per annum over a couple of decades and more. This has been driven largely, or associated largely with reductions in the cost. And the market that we see is increasingly dominated by crystalline silicon technology. If we want to meet the low carbon targets expressed by net zero or other mitigation pathways, we rely on PV to continue to grow. And so we need to ask the questions, what are the factors that could limit the future growth in PV? Next slide, please. So we can identify three areas. One to do with the fact that solar is a variable resource, and so there's a danger of oversupply when the power can't be used. That reduces increases the overall cost and reduces the value of the power. Then there are issues to do with the cost of the technology and to what extent that can reduce. That's a function of the module, but also of the way that it's integrated into the system. And then there are regulatory issues that will influence how fast and in what way the technology can grow. Next, please. So these involve, some of these involve issues for material science, not all. The cost of the PV technology particular is influenced by factors such as the electronic and optical quality and the stability, not only of the semiconductors that we use to harvest and convert the light, but also the materials that we use as contacts, as electrodes, as optical coatings and the materials that we use as parts of the system. Next, please. But there are also materials science issues for the associated technologies which we will depend on in the end for integration of PV into the energy system. Claire mentioned the need for stable and high performance battery materials. Storage is a very important part of integrating PV. Then there are also the associated technologies of transmission, distribution, and the use of solar power, for example, in fuel synthesis, in transport, and so on. Some of these issues will be addressed later in this talk. Next, please. So thinking about PV in particular, and coming back to the road mapping exercise that Neil talked about, there's a number of directions in which we could go from the state of the art, which is crystalline silicon, which currently dominates about 95% of the market. And one obvious way to go is to try to make crystalline silicon technology better and cheaper by working on the manufacturing and the design of the crystalline solar cell to improve its cost effectiveness, extend its lifetime, and improve its efficiency. Next, we can also go in the direction of trying to make silicon better by adding something to it to increase the overall efficiency. And that could be, for example, as Julia Brown mentioned, a clever optical coating, which is allowing us to harvest more of the solar spectrum by down converting or even up converting some of the light that isn't efficiently captured by a solar cell. Or more obviously, it could be a second semiconductor layer, which acts as a second solar cell with a different larger band gap device to form a tandem and increase efficiency. Next. Or we could make a device which is inherently more efficient by using multiple gaps and not constrained by silicon. We could, for example, look at other material systems. Next, or if we go in a different direction, we could, rather than trying to increase efficiency for the sort of standard market, we could look at where PV can be used in other markets where different properties that aren't easily met by crystalline silicon are needed. For example, where you want to integrate transparent solar cells into buildings, or when you want a very light or flexible solar cells for use in unusual applications. Next, and probably most importantly of all, we should think about how to reduce in cost and improve overall performance by integrating the solar cell into other functions. For example, integrating a solar cell device with a catalyst for fuel synthesis, with a battery for any type of application where you wish to store and reuse the power. So I'm going to give just two short examples from this list. Next, please. And next again. The first example is to take something which is actually being developed and commercialized in the UK, the idea of putting an extra layer on top of silicon to turn, say, a 24–25% silicon solar cell into maybe a 27 or higher percentage tandem device. And that can be done by using a layer of a perovskite PV technology. Perovskites offer band gaps which are reasonably good to the optimum to make a tandem with silicon. And to do that, to do it efficiently and well, then there's a number of issues for material science. They're to do with controlling the defects in the perovskite, with trying to minimize the lead content, and then also work to do on the silicon, to do with its design, to do with improving the compatibility of its surface with the layer that will be deposited on top. And then we need to think about the manufacturing process, and to make sure that both in manufacture, in recycling, and in use, exposure to toxic components is minimized and the overall embedded energy is reduced. So that's one sort of specific challenge. Next, and next again. So the second example I want to give is where solar cells could be used in non-conventional markets. And for example, there's a growing demand for PV to power small components, mobile components, for example, in Internet of Things. There's also another area, which is the use of solar power for satellites, for example, for the growing communications industry. That's a relatively high value industry, and the first IoT is something which is growing very, very rapidly. And here, because of the very different conditions in which the solar cells would be used, you have different requirements. On the semiconductor itself, for example, optimization in different spectral conditions, and also on other factors that we don't normally consider, like the power to weight ratio of the silicon solar cell, its mechanical toughness, and then of course we need to consider the usual issues of lifetime and production cost. Next. And again, these introduce issues from material science, but they're rather different issues than the ones that we would need to consider, for example, in improving silicon, or for example, in putting perovskite on top of silicon. But they relate to properties of the semiconductor, design of the overall device, and of course the sustainability and embedded energy in the manufacturing process. So I'm going to leave it there. I'll be happy to take questions later. Thank you.
Thank you very much, Jenny, for that excellent talk. Now, it's my pleasure to introduce Professor Nora Delou. She's a professor in computational chemistry and the executive dean of the Faculty of Engineering and Physical Sciences at the University of Leeds. She's a fellow of the Royal Society of Chemistry and Learned Society of Wales and member of Academia Europaea. Her research encompasses materials for biomaterial applications and sustainable energy materials. So over to you, Nora.
Thank you very much for that introduction. I'd just like, with my computational background, like to show that computation, for instance, has quite a role to play in designing and improving sustainable energy materials. I mean, very much based on the concept of the Materials to Genome Initiative in the United States, where it was shown that if you introduce computation in a series of experiments, that you get products have a much shorter time from the lab to the shelf, so to speak. So I'd like to just show a few examples of where computation can help experiment and can actually be truly predictive as well in designing and developing new materials for sustainable energies. The reason I'm picking iron sulfides here is because, as we have already heard, there is a great need to look at materials that are based on readily available elements. And of course, both iron and sulfide are readily available and therefore cheap, and we will not be, and geopolitically, they're in stable countries. So could I have the next slide, please? So we had a look at a couple of iron sulfide for a number of reasons. First, there's an intriguing origin of life theory that posits that iron sulfide particles that were created in black smokers, either alkaline black smokers or acidic black smokers in the archaic ocean, created these tiny little iron sulfide nanoparticles, and these were actually the catalysts in the origin of life. So they were catalysts for converting dissolved CO2 into small biological molecules, although it was prebiotic, so small organic molecules that eventually led to life evolving from the sea. Now, whether this is true or not, we don't know, but it's an intriguing concept, and we thought that iron sulfides, for many reasons, are interesting to look at. Another reason is because they have, in enzymes, you have reactive sites that are based on cubane iron sulfide and iron nickel sulfide cubane particles, where a lot of the electron transfer takes place, or again, which act as a catalytic site. So based on these two examples, plus the fact that, of course, iron sulfides with their multiple valence sites are very good electron cycling materials. So we were interested in looking at these to look whether we could convert CO2 into useful chemicals or synthetic fuels, which of course would be help a lot in a carbon net zero future. Could have next slide, please? So of course, one of the reasons why we looked at these materials was because they would be quite good for modeling, both modeling and experiment. And we were mainly interested here to also solve a problem in the literature, whether the alkaline or the acidic fence would be the best for this origin of life theory. So we started with the calculations looking at the 3 types of carbon dioxide molecules that exist in these 3 pH regimes. So in a very acidic medium, you would have dissolved CO2. And we absorbed those and calculated the binding energies to two major surfaces of these tiny mineral particles, the 001 and the 111 surface. And then at pH 6.5, you would have bicarbonate, that would be the main species, and at a very high pH, it would be a carbonate molecule. So we then attached all these molecules. Well, we did some calculation of these molecules binding to these two surfaces. And if you look at the energies, you see that the bicarbonate and the carbonate both attach to the 111 surface and also to the 001 surface. However, in an aqueous medium, of course, it's a competition between the carbonate molecule and the water molecule. So if you look at the binding energy of the water molecule, it is from those comparisons clear that only the 111 surface, the bicarbonate molecule, can actually displace the water molecule from the surfaces, and therefore that should be the only catalytic regime where you could convert the CO2-based molecule to something else. Grab next, please. Then we did the calculations of the mechanistic catalytic pathways, and starting from the adsorbed molecules at the surface, you go through a lot of intermediates. So this is actually a good slide to show that we need a lot of computing power. I mean, computing is obviously always thought like, well, it's a cheap technology. You don't need very heavy lab-based equipment, but you do actually need quite a lot of computing power. And we're fortunate in the UK that we have that through the Archer 2 and its predecessors, National Computing Facilities, which is a real help to make the UK internationally competitive on computational sciences. So we then calculated all these intermediates, and we calculated pathways, and then what we calculated was that you can get through the mechanisms within a reasonable voltage of about 1 volt, which we wanted to stay in a reasonable energy regime, so that this is a process that could be powered by solar energy, for instance. You could get both methanol and methanoic acid, which are very good either a fuel or a chemical itself, or a very good precursor to a lot of known pharmaceuticals, fuels, etc. Next slide, please. Of course, in the end, the proof of the pudding is in the eating. So we did experiment as well to see whether with these new, these novel catalysts, we actually did get products that we were looking for. And you can see already that the calculations were right in predicting that at pH 6.5, we would get the best catalytic performance. And you can see that we do indeed produce methanol and formic acid, but more interestingly, we also form CC bonds and have both pyruvic acid and ethanoic acid forming at pH 6.5. This is particularly interesting because pyruvic acid is accepted as a small organic molecule that is imported on the pathway to bigger biological molecules. Next slide, please. They've got a very quick, I promise it will be very quick, an example of another work where we worked with experimental colleagues in Eindhoven University looking at iron pyrite, another sulfide material for photocatalysis. It should be a really good photocatalyst, but it has experimentally shown limitations, even though theoretically its potential would be very good. Next slide, please. Now, originally, it was often thought that marcasite, which is the same composition but a slightly different structure, if you get inclusions in pyrite, that would bring down the potential of pyrite as a photocatalyst. Because an early experiment had shown that the band gap in marcasite is much lower than the band gap in pyrite, and therefore would make the material less well performing. However, recent theory and experiment both shown that the band gap in marcasite is actually much higher and similar to pyrite. So there is no reason why marcasite should have a negative effect on the pyrite material. Next slide, please. So we did an experiment, or rather my colleagues in Eindhoven did an experiment, and they showed that indeed if you have pure pyrite, which is the green curve, you have a moderate response to as a photocatalyst or photoelectrochemical material. However, if you have a mixed phase, I mean, they created two mixed phases at two different temperatures, the red and the blue, and you can see that particularly the red phase, which was synthesized at 380 degrees C, has a much better response, photo response, than the pyrite material. So then the next slide shows some calculations be done to explain this, and then look into why this could be the case. And when you do the alignment of the band gaps of the pyrite and the marcasite, so you take into account the vacuum level, and then you just basically align the gaps, what you find is that you get this type of setup, where if you had a photo excited electron, for instance, in marcasite, it would go to the conduction band, but because of the different alignment of the two materials, it would then actually flow into the conduction band of pyrite. Whereas if a hole is created in pyrite, it actually flows to the valence band of marcasite. So you get a very effective separation of the two charges, which is what is necessary in a good photoresponsive material. So in fact, the modeling here shows what was shown experimentally, or explains what was shown experimentally, that actually if you have a mixture of marcasite and pyrite, you should get a much better photoresponsive material rather than the initial. So that was just the two examples I wanted to very quickly show, and I hope I haven't gone too much over time. Next slide, please, just to acknowledge the people who did the work. So Alberto and Nelson for the modeling, and Nathan and Longfei for the experiment. And thank you very much for listening. Thanks.
Thank you, Nora, for that very nice talk. So it's my pleasure to introduce the last speaker of the plenary session, Professor Stuart Parkin. He's an IBM fellow, an expert in magnetoelectronics and spintronics. Stuart is the director at the Max Planck Institute of Microstructure Physics in Halle, and a professor at the Institute of Physics at Martin Luther University in Halle-Wittenberg. He was awarded the Millennium Technology Prize in 2014 for his work on spintronic materials. So on to you, Stuart.
Thank you very much. I'm very pleased to say a few words about how we could potentially build more efficient electronics beyond today's systems which are based on charged currents. I'm just going to make a few comments then about potentially using spin currents and ion currents to build more energy efficient storage and computing technologies. So if you go to the next slide, then of course we're in a super exciting era of the silicon MOSFET, and over the last 40 years it's enabled orders of magnitude improvements in computing power. In other words, we can compute much more efficiently in terms of the cost. And so this has led to an enormous improvements in our ability to, for example, to collect and analyze digital data, and it's really fundamentally changed the way we live. However, the concept of the silicon MOSFET has been to simply scale a device to smaller and smaller dimensions. And we've reached a point where in order to do that, we need to use increasing amounts of energy, so much energy that it becomes impossible. So the conventional rules of scaling CMOS devices, which have enabled these enormous improvements in computing power, essentially ended about 10 years ago, when we can no longer increase the frequency with which we operate transistors. So today, there are two main areas of very interesting research that could enable us to go beyond the charge-based CMOS electronics. And these, I think, you can imagine are quantum computing, and quantum computing uses very different principles, and a whole variety of quantum bits have been evolved over the last few years, including spin qubits, ion traps, and the leading technology today is superconducting qubits. However, quantum computing is likely to require today very low temperatures, and it's not something that we might imagine to be in everybody's pocket. However, at the same time, quantum computing is perhaps restricted in the types of problems that it could solve, although it could solve these with massive computing capability. Another very interesting area is what we might call neuromorphic computing or cognitive computing, where we imagine that biologically we can compute 1 million times more energy efficiently per computing operation than today's CMOS transistors. And so can we build new types of devices, new types of systems of devices that would be based on principles from nature? And this is very interesting and very exciting. And the concept is we could build a computing system then that would use 1 million times less energy to carry out the similar computing power. Again, the problems may be more restricted, but nevertheless could solve many of the computing problems that are important for our lives. So I like to call this possibly human computing era would begin. So my points today is that to do this, we probably want to go beyond the charge and perhaps consider spin currents, or we want to go beyond the charge and consider ionic currents. And I think another very important point is that today's computing devices, both for computing, for memory, and for storage, magnetic storage, are all innately two-dimensional. You have a sheet of transistors, or you have a sheet of magnetic bits. We want to build devices that are more innately three-dimensional. I think this will be a very important principle going forward. So if you go to the next foil, let me just briefly touch on spintronics. So spintronics is the notion that in Hürter structures consisting of alternating layers on the electron scattering length scale of metals and insulators, non-magnetic and magnetic materials, we can build structures in which we can control the flow of currents of electron spins. An electron spin current innately can carry no charge, and therefore it can be dissipationless and therefore use much less energy. And the first device that uses the control of spin currents, or at least spin-dependent scattering of electrons, is something called a spin valve that I played a key role in inventing 30 years ago. And this has been used in magnetic disk drives to sense tiny magnetic fields, because it's basically the most sensitive detector of tiny magnetic fields that is known at room temperature. Although originally the principle was that of spin-dependent scattering, that giant magnetoresistance, the principle now has evolved to what is called spin-dependent scattering. And on the right-hand side of this foil, you can see what's called a magnetic tunneling junction. The blue and red layers are magnetic layers, and the gray layer is an insulator. The electrons can tunnel from one magnetic layer to the other, and depending upon the relative magnetic orientation of these two layers, the tunneling current can be high or it can be small. And today at room temperature, you can see changes in current when you change the relative orientation of these magnetic moments of the two layers of about a factor of, up to a factor of several fold. This concept of a magnetic tunneling junction then is very interesting. You have a device with two states which is non-volatile because it's determined by the magnetic moment of one of the layers, and yet the difference in the resistance of these states can be so large that it can be detected on very short timescales. This is the principle of something called magnetic random access memory, and it's something that we proposed in 1995. So on the next foil, I just wanted to give you some sense of how long it takes for a new physical phenomenon or even new material to make its way from the laboratory into a technology. On the top is just a time chart of how long it took to take what was the discovery of giant magnetoresistance, a very large change in resistance, but in very, very large magnetic fields at low temperatures. So it's not technologically relevant. But I was able to show we could see a similar phenomenon at room temperature in fields that were 10,000 times smaller and make it technologically relevant by using a phenomenon called spin engineering. We use the concept of coupling of individual magnetic layers through metals to create entirely new structures. We call them synthetic antiferromagnets. It only took a few years before we could take fundamental discovery to a product that could revolutionize magnetic disk drives, enabling their capacity to increase by 10,000 times in the last 20 years. Although even that technology now, it's reached the end of its roadmap. But on the other hand, if we take this concept I briefly mentioned of magnetic random access memory, which is based on really a spintronic phenomenon, we proposed this in 1995, but it was only last year, more than 20 years later, that Samsung announced the shipment of a high-performance foundry magnetic random access memory technology. It turns out it's an embedded memory technology. And another very important principle of this spintronics is that we could use spin currents to generate spin angular momentum to rotate magnetic moments. And this is the principle of writing these devices. It's called spin transfer torque. If you go to the next foil, I want to briefly mention what I think is a super interesting new concept. It turns out I also proposed this. But anyway, I called it magnetic racetrack memory. And I proposed this about 10 years ago. And the concept is that this will be a three-dimensional memory where you have billions of vertical scanning nanowires And in this magnetic nanowire, we would store information in the form of magnetic domains, pointing in one direction or the other direction. And the basic principle is by passing a current through this racetrack or this nanowire, we can move the information backwards and forwards. So this would be a three-dimensional storage class memory capacity of a magnetic disk drive, 1,000,000 times faster, 50 times less volume, and much more energy efficient. So if you go to the next foil, I'm going to not say much about this. If you go to the next foil, you will see that we have evolved this concept from 10 years ago through several stages of discovery, where we've discovered totally new principles that actually make it even more interesting than we thought, and we can manipulate magnetic domain walls in these nanowires 10 times more efficiently than we had imagined 10 years ago with new principles of science. If you go to the next foil, maybe I just make a couple of points about another concept, which is going back to this concept of neuromorphic computing. Just a general point, the way we build computing systems is very different from the way we think. Fundamentally, we think in a very parallel form. We integrate memory and processing in single devices or networks of devices, whereas conventional silicon-based systems are individual devices for memory and for processing, in fact, several types of them connected together, which causes significant energy usage, whereas the brain is much more energy efficient and is great for certain types of problems. If we go to the next foil, then just wanted to make the point that this concept of cognitive computing, many different ideas, even the magnetic tunneling junction can be built as a synaptic device to connect neurons, artificial neurons, but there are many other proposals over the last few years, many of them based on charge-based devices, but some based on spin-based devices, some based on ion devices. This is like an emerging field that could lead to hugely low loss energy electronics. If we go to the next foil, then I just wanted to conclude by saying I think there's a lot of opportunity to build low energy electronics by going beyond charge, by using spin currents, and by, for example, to build racetrack memory, by actually something I didn't discuss, but there are enormous numbers of new chiral spin textures that have been discovered in the last few years, which are very interesting to build, for example, a reservoir type of computing with regard to cognitive computing. And I think building synaptic functions in not individual devices, but looking at systems of devices connected in a three-dimensional way to look at their emergent properties will lead us to highly energy efficient thinking devices in the next few years. That was the end of my talk. Thank you.
Thank you very much, Stuart. Could I thank all of the plenary speakers for their excellent talks.
So in this next session, we're going to have speakers to introduce the road mapping areas. So just to recap some of Neil's very earlier introduction, the motivation behind what we're presenting today is the UK passing emissions law to become net zero by 2050. And this graphic here just shows which are the key areas which, if we could tackle, we can make a major inroad into doing that. And that's the residential, energy supply, transport, businesses, and also agriculture. Next slide, please. In this road mapping exercise, we chose to study 4 key topics, and that is the future of materials in photovoltaic systems, low carbon methods of hydrogen generation, decarbonisation of heating and cooling, and low loss electronics. And the graphic on the right just shows how the primary energy is used, with 40% of being used in electrical energy. Next slide, please. So where are we on the timeline? Well, as Neil mentioned, we conceived the idea in September last year and started to work with the Institute of Physics in October. And the Institute of Physics sent out a survey to which we had 272 responses from the community, and which then led into our online workshops in partnership with the Institute for Manufacturing. Today we're at the launch of the key findings, And following these, there will be a period of refinement of these roadmaps during July and August, prior to the publication of the full roadmap in September. Next slide, please. So we now have a series of 5 talks in the area of photovoltaics, hydrogen production, thermal electronics, calorics, and low-loss electronics. Next slide, please. And I'd like to introduce the first of our speakers in this session, Dr. Robert Hoy. Rob is a lecturer in materials at Imperial College London. He leads a group working on developing defect-tolerant semiconductors with a particular focus on their applications in photovoltaic devices. Over to you, Rob. Thank you.
Right. Thank you, Rich. Can we have the next slide, please? Okay, photovoltaics are devices which produce clean electricity from sunlight, and that makes them an important source of renewable energy. In the UK, we need to accelerate our deployment of this technology from 13.5 gigawatts today to over 200 gigawatts by 2050 to help us to meet our net zero carbon targets. By increasing our investment in this technology, it's not only important for the climate, but also important economically. Worldwide, the solar cells market is worth over £100 billion, and that's predicted to steadily increase exponentially in the future. Now, we can use solar cells not just at the utility level, but we can also use them for energy harvesting windows, as well as indoors to power an increasing number of small wireless devices, which are part of the Internet of Things. And these emerging markets in building integrated PV and indoor PV also set to very quickly grow in the future. So it's very important that in the UK, we can increase our presence in these markets to reap the economic benefits as well. Fortunately for us, we have a very active academic and startup environment in the UK, but currently it's very challenging to commercialize new solar technologies. So the focus of our roadmap is on the future of PV materials research, and it's not just how we can achieve carbon neutrality by 2050, but also how we can be more competitive in these solar markets. Can we have the next slide, please? So our roadmap involves a consultation from people from 14 academic institutions and national labs, as well as 10 UK-based companies. And we had 9 sub-roadmaps, and these span all the way from challenges in industry to materials that we use at the utility scale, right the way through to technologies and materials that can be used in emerging markets. So can we have the next slide, please? So across the 9 sub-roadmaps, these were the 4 main research challenges. The first is that we need to have a better understanding of what processes are limiting the efficiencies and the stability of both existing and emerging solar absorbers. And we need to find ways to overcome these lost processes. So this involves a combination of both fundamental and applied research, such as the development of new charge extraction layers. We also need to work on scaling up new technologies. And this involves not just working at the cell level, but also working at the module level. And for example, we need to develop new large area manufacturing processes, as well as more sustainable ways of manufacturing module level devices. We also need to extend the lifetime of solar technologies up to 40 years. And this involves developing better encapsulation materials, as well as developing new protocols for the accelerated testing of the degradation of new materials. And across all new technologies, it's very important that we can develop new electrodes, both transparent and opaque, which are not reliant on expensive or scarce elements. In other words, going indium-free and moving away from gold and silver as contact materials. Next slide, please. The opportunities, if we can do this, are first of all developing solar cells which can be manufactured using low capital intensity methods and which have extended stability. An example of a new type of device that's really promising are multi-junction solar cells, which combine a metal halo perovskite with a silicon bottom cell, and this can deliver efficiencies over 50% greater than current silicon technologies. We can also achieve carbon neutral buildings by using the cladding of buildings as energy harvesters rather than as passive layers. We can also develop new lightweight and flexible solar cells that can work indoors to power standalone devices, or which can be used to power electronic vehicles, as well as be used for aerospace applications. And these new technologies can also be enablers for other renewable sectors, such as which rely on the clean production of sunlight from clean production of electricity from sunlight. And examples include the splitting of water to make fuels, as well as the generation of ammonia. Next slide, please. So the requirements for doing this is first of all having dedicated funding for PV materials research and both fundamental and applied research. Right now we have central facilities for certifying the efficiencies of solar cells. We also need to have dedicated central facilities for advanced device metrology and the testing of the degradation of materials. We also need to have catapults and pilot facilities to accelerate the scaling up of new technologies. And this includes having a pilot production line for silicon solar cells where we can test new device structures as well as custom make silicon for applications in new devices such as in multi-junction devices. And we also need to have consortia that can bring together the key people. That is the people doing the research, the manufacturers, the funders, and the people in the end user industries who can tell the people doing the research what's really needed by the consumer. And finally, we need to build up a pipeline of skills in this area by having centers for doctoral training, as well as training networks for postdoctoral researchers, as well as people in industry. And in doing so, we can achieve energy security for the UK, where we can supply our own renewable energy needs using solar cells manufactured in the UK. And this will create new jobs, and we can fill those jobs using locally sourced people. Thank you.
Thank you very much, Rob. So our next speaker this morning is Dr. Ivan Evans. Ivan was appointed Senior Lecturer in the Department of Materials at Imperial College in 2017. Prior to that, he was Associate Professor at the Technical University of Denmark. His group investigate catalysts for low-temperature electrochemical devices for the production of fuels and valuable chemicals, leveraging insight from model experiments to discover new materials. Over to you, Ivan.
Thank you for the introduction. Let's move to the next slide. So as Dame Julia King highlighted earlier today, hydrogen could play a key role in areas where we make the largest amount of greenhouse gases, such as transport, energy supply, business and residential. So hydrogen is potentially zero emission energy vector and chemical feedstock. For instance, it could be produced using renewable electricity by electrolysis, then converted back to electricity with fuel cells. So the demand for hydrogen is set to increase by at least a factor of 10, both in the UK and globally. However, what's important to bear in mind is that hydrogen right now is not sustainable. So 95% is from steam-reformed fossil fuels, only 5% from electrolysis. So right now, the current production makes enormous amounts of CO2. So we want it to be more sustainable. So let's move to the next slide. So we did the consultation of 20 academic institutions and national labs and 6 companies looking at developing new materials for hydrogen. So move to the next slide. So we have identified 6 technologies where the UK materials community can really make an impact. So we look at these first 4 technologies, all different kinds of electrolyzers. So on the right, you have a schematic of a proton exchange membrane electrolyzers. So all of these technologies, I've proposed different opportunities and challenges and different degrees of technological maturity. However, common to all of them, you either need better catalysts, as shown in the insets on the top right here, or better electrolytes or better electrodes, or a combination of all 3 of those. So regardless, materials play a critical role. So right now, hydrogen is used to produce chemicals like ammonia or ethanol in large-scale thermochemical reactors at high pressures and high temperatures. That's a very steady state. So if you get electrolytic hydrogen from solar and wind, it will be produced at low pressures at constantly varying rates. Hence, we need new catalysts and other materials that operate at low pressures and low temperatures for thermochemical synthesis. Alternatively, we could do away with molecular hydrogen altogether and produce these chemicals by the direct reduction of nitrogen or CO2, as Nora discussed earlier. Again, we need better catalysts, electrodes, and electrolyte materials. So it's important to emphasize actually the advances and methods and understanding that we use for one of these technologies are often directly transferable to the other technologies. Likewise, as Jenny and Robert emphasized earlier, improvements in electrolytic energy storage improve the viability of solar power for instance, by decreasing the impact of the intermittent supply of solar or wind. Likewise, materials used in solar cells could also be used in photoelectrolytes. There's a lot of cross-cutting activities that would benefit all these different areas. So let's move to the next slide. So what we require is state-of-the-art facilities, world-class scientists and engineers, and a lot of integration across the UK and academia and industry, and also strong integration into international partnerships, research programs, and value chains. So one thing that we came out of our road mapping exercise, we noticed there's a big discrepancy between lab scale testing in academic labs and the full cell electrolyzer testing that's done on the stacks in the industry. So material that works well on the lab scale doesn't necessarily work right now well in industry. So we need routes and facilities for the testing of new materials at single cell prototype level to bridge this divide. So move on to the next slide. So there's enormous opportunities for the UK in this area. We already have really leading companies in electrolyzers and fuel cells, and also production of materials and catalysts for hydrogen production and fuel cells. So we also have enormous potential for renewable electricity, particularly for offshore wind, as you can see in the figure on the right. And hydrogen allows us to store this. So hydrogen is particularly attractive, again, as Julia King mentioned before, for decarbonizing some of the areas that are most difficult to decarbonize, such as heavy-duty vehicles, or for heating, or for an industry, for production of steel, methanol, and ammonia. So if we build up a strong homegrown industry in the UK for hydrogen, we can become Europe's leading exporter of hydrogen. Thank you for listening. I'll now pass the floor back over to Richard.
Thank you very much, Ivan. Next slide, please. So our next speaker this morning is Dr. Oliver Fenwick. Ollie is a Royal Society University Research Fellow and lecturer in materials science at Queen Mary University of London. He's an expert in materials for plastic electronic devices, and since 2015 has been developing materials for flexible and printable thermoelectric generators. Over to you, Ollie.
Thank you for the introduction. Next slide, please. So thermoelectric technology concerns the conversion of thermal energy in the form of temperature gradients into electrical energy and vice versa. So these are semiconductor devices that can therefore be used as electrical sources of heating and cooling, or to convert waste heat into electricity. The diagram shows on the left the ways we produce energy, and on the right how we use it. So it indicates that about 2/3 of the primary energy is wasted as heat, making technologies that can recover this waste heat rather important for the future. Next slide. We should not look at thermoelectrics in isolation, of course, and there are possibilities to use other heat engines or to store the heat for use elsewhere. It can be transported or converted to electricity using thermophotovoltaics or thermoelectrics. So some of the advantages of thermoelectrics lie in the lack of moving parts, their semiconductor devices, and high reliability. Thermoelectric generators made with different materials are available over a temperature range from over 1,000 degrees Kelvin down to room temperature, noting that near room temperature is where the largest amount of waste heat is generated. Next slide, please. The maximum heat to electricity conversion efficiency of a thermoelectric generator is determined by the figure of merit, ZT, of the material it is made of. We currently have materials with this figure of merit around about 1, putting us on the lowest efficiency curve on this figure on the right. With this performance, we can only expect to get energy conversion efficiencies of a few percent at moderate temperatures. If we could develop materials with this figure of merit more like 3, we could be looking at 20% conversion efficiencies, for example, which is becoming competitive with other technologies. Nonetheless, there are already applications for thermoelectrics in so-called Peltier cooling devices, which are refrigerant-free and have no moving parts. There are also applications for recuperating industrial waste heat, and the concept has been explored in the automotive sector to improve fuel efficiency, again by a few percent. Next slide, please. The figure of merit, ZT, is a material property and has proven challenging to optimize, despite the fact that there is no real theoretical limits for ZT. So indeed, the diagram on the right shows that our best materials had this figure of merit round about 1 from about 1960 until the turn of the century. However, since then, there's been a rapid improvement as our understanding of thermoelectric materials has developed, and the highest recorded ZT values are now over 2.5. In addition, a number of other classes of thermoelectric materials are rapidly emerging, promising breakthroughs either in performance or processing or cost. Next slide, please. So this road mapping process, which has involved 3 companies and 10 academic institutions, has focused on a range of thermoelectric materials, from the most established, like the chalcogenides, to those with new and emerging physics. Next slide. We focus primarily, but not entirely, on the materials challenges, since a step change in the figure of merit in the medium term would open up vast new applications for thermoelectrics. However, there are also many applications that can be accessed in the near term through development of thermoelectric generators incorporating materials of proven performance. Nonetheless, it's in materials with new physics that we can search for a step change in energy conversion efficiency. That is, aiming for these figure of merit values greater than about 3. We can also consider developing materials that avoid the use of rare elements, such as tellurium, that is currently widely used in thermoelectric devices. Next slide, please. So the research challenges themselves includes developing a more complete understanding of structure property relationships at the nanoscale, including heat and charge transport across interfaces and in amorphous regions in materials. This is an experimental and computational challenge. We would still benefit from improved accuracy of thermoelectric property measurements, and device prototyping will be important for developing new applications, improving efficiency, of course, and for incorporating new materials into devices. Scale-up issues include abundance and cost of materials, as well as a full life cycle analysis where new materials are introduced. So all of this, of course, requires close cooperation between academic and industrial partners, and in the UK, we have plenty of both. Next slide, please. So the opportunity is to move thermoelectrics from a relatively niche technology to something that is broadly applicable and can deliver significant improvements in energy efficiency in key industrial, residential, and transportation sectors. A step change in ZT could deliver a huge market expansion in waste heat harvesting and heating and cooling technologies, which would create opportunities for existing UK companies working in this area, as well as end users. Thank you very much for your attention.
Thank you very much, Ollie. So just before I introduce the next speaker, just to remind delegates that you can send your questions in using the questions function on the right. After this session, we will be having a Q&A session. So next slide, please. Next speaker in this session is Dr. Javier Moya. Javier is a Royal Society University Research Fellow at the Department of Material Science in Cambridge. He's an expert on caloric materials and devices for environmentally friendly heating and cooling. He is also founder and director of research at Baracal Limited, a startup company that is commercializing barocaloric materials and systems. So over to you, Javier.
Thank you very much, Richard. Heating and cooling are essential to our lives. We rely on them for comfort in our homes and vehicles, and businesses need heating and cooling for productive workplaces and industrial processes. Taken together, heating and cooling represent the biggest contribution to our energy consumption and the biggest source of greenhouse gas emissions, as can be seen, on the next slide, on the chart on the right. The space heating of buildings, which is provided primarily from burning of natural gas, and space cooling of buildings, which is provided primarily from compressing volatile greenhouse gases, represent the largest contribution to our heating and cooling needs, and on their own account for 17% of the UK CO2 emissions, as highlighted again in the chart on the right. However, these technologies are not efficient neither friendly to the environment. A completely new approach on the way we heat and cool that is not based on the use of harmful gases is therefore required if we are to reach the 2050 zero carbon target. Moreover, given that 20 million homes and businesses in the UK are connected to the gas grid, ensuring this transition represents a major national challenge over the coming years. Caloric materials that displace large changes in temperature when subjected to changes in applied field can provide a solution for zero carbon heating and cooling that is both energy efficient and environmentally friendly. Next slide, please. Traditional heat pumps and air conditioners exploit phase transitions in fluids between a gas phase and a liquid phase in order to achieve heating and cooling. When sufficient pressure, which is labeled fill in this diagram, is applied to the gas, which is labeled phase 1, the gas transforms into a liquid, which is labeled phase 2, and energy is released, thus increasing temperature, as can be seen at the bottom of the schematics. When pressure is removed, the liquid transforms back to the gas phase and energy is absorbed, thus decreasing temperature, as shown in this case at the top of the schematic. Then, by repeating this cycle over and over, we can achieve heating and cooling. Caloric materials operate under the same principle, but instead of exploiting a phase transition between a harmful gas phase and a liquid phase, the material always remains solid and therefore does not pollute the atmosphere. Next slide, please. With this motivation, a roadmap consultation on materials under the aegis of the Henry Royce Institute was conducted with the participation of 8 academic institutions and 2 companies, all of which are listed here. After this consultation, key challenges and opportunities have been identified, which I will describe in the next slides. Overall, for this technology to succeed, research is needed across all technology readiness levels, both in academia and in industry. Next slide, please. The 4 strands of caloric materials, that is magnetocaloric materials driven using magnetic field, electrocaloric materials driven using electric field, elastocaloric materials driven using stress, and barocaloric materials driven using pressure, present different challenges, which are listed here. This is partly because of the different nature and partly because of the different level of maturity. Less prototypes exist for the bottom materials, but there is plenty of optimism for this, given that the thermal response is extremely large and for the first time comparable to the thermal response of the gases that are currently used in existing heat pumps and air conditioners. And moreover, there is plenty of room for discovery of materials with even better performance. For magnetocaloric materials, key challenges are reducing cracking under magnetic field in order to extend operating life, and reducing the magnitude of the driving magnetic field in order to reduce cost of permanent magnets. For electrocaloric materials, key challenges are improving fabrication of multilayers and increasing breakdown field in order to achieve larger thermal capacity. For elastocaloric materials, key challenges are reducing materials fatigue and increasing breakdown stress in order to extend operating life. And for barocalorics, key challenges are reducing histolytic losses and reducing driving pressure in order to obtain materials that bring down the cost of compressors. Next slide, please. The opportunities are huge. The combined world market for space heating and cooling of buildings is large, and this market size doubles when incorporating other heating and cooling applications such as domestic refrigeration and commercial refrigeration, yielding a total of £300 billion with projected annual growth of between 5 and 10%. The achievement of heat pumps and air conditioners and related appliances such as fridges that operate using caloric materials instead of gases will permit decarbonizing heating and cooling, provide energy independence, and enable the UK to become the world leader on this emerging technology. Ultimately, this will permit reducing our greenhouse gas emissions while growing the economy and will secure our energy, environment, and jobs. Thank you very much.
So thank you, Javier. So next slide, please. So our final speaker in this session, before we have questions and answers, and just to remind you, please send those in using the questions function. So our final speaker is Professor Edmund Linfield. Edmund is chair of Terahertz Electronics in the School of Electronic and Electrical Engineering at the University of Leeds. He is director of the university's Bragg Centre for Materials Research and co-champion of the Henry Royce's Atoms to Devices theme. Over to you, Edmund.
Thank you very much indeed, Richard. We've heard already about how materials provide solutions for energy generation, for energy storage, energy recovery, and heating and cooling. But we now want to look at how we can use materials to reduce the energy losses in electronic devices. Next slide, please. If you look on the left-hand side here, you can see a whole range of things from the consumer products based on the transistor, the portable electronic devices we have, through to electric drives in vehicles, all the way through to the grid. And the electronics industry is enormous internationally, with over 600 billion pounds worth of markets. And similarly, the power electronics industry is over 100 million pounds, and these are growing year on year. But one of the problems we have is, of course, with this growth comes energy usage. And already 5% of the world's energy is used in digital technologies, and this is expected to reach over 20% by 2030. And it's also notable that the UK has a relatively small component of that global electronic sector. So the question we're thinking about is, how do we simulate the UK economy in the electronic sector? How do we meet consumers' expectations for bigger and better electronics? But at the same time, how do we meet the government's net zero greenhouse gas emission targets by 2050? Next slide, please. We undertook a road mapping with more than 50 participants, and with industry represented by the wafer fab companies, the equipment manufacturers, and by a series of end users. And we looked at research in 3 principal areas. Next slide, please. The first was power electronics, how we control the flow of electrical energy from the source, for example, wind energy or photovoltaics, through to load and where we use it, and the use of power electronics in things like electric vehicles. And the first thing that was really clear from the roadmaps was the need to find a way to take the excellent research done by academic institutions in the UK and scale this up. We need a pipeline for industrial exploitation through pilot lines, through to wafer scale and to manufacture. It's also clear that we need to be able to innovate in the current devices used for power electronics based on gallium nitride and silicon carbide materials. The right-hand figure just shows the advantage of moving from silicon to silicon carbide in wind generation and how you can reduce the power loss quite significantly just by that change of materials. But more importantly, we wanted to think about what was going to happen beyond gallium nitride, what was going to happen beyond silicon carbide. What were the next generation of materials for power electronics? What will we be using in 2050? And in doing that, we thought about the availability of materials and avoiding using materials that are scarce. We've already heard mention of gallium being one of those. How we recycle our electronics devices, and then how we look at the full energy cost of those devices, not only in the manufacturing stage, but also their whole life usage. Next slide, please. The second area we looked at was going beyond CMOS, the current technology we use in all our computers. If you look on the diagram on the right, we want to move to the bottom left-hand corner where we see the red star. And in order to do that, we looked at different things we could do with the transistors in terms of different variations of the channel and also the style of way that the transistor worked. But at the same time, we realized that as well, we could try and get CMOS to do more for ourselves by combining those transistors with things like sensing, energy harvesting, and RF devices. And that meant mixing the CMOS capability with things like photonic, magnetic, piezoelectric, plasmonic materials to get additional functionality with the devices we have now. So those are the first 2 areas we looked at in the road mapping exercise and things that have input on manufacture now. The third area, though, and this has been very well introduced by Professor Parkin this morning, next slide please, was what are we going to do beyond the current materials and devices we have? Going beyond CMOS into what's called more than more, beyond Moore's law, which has helped dictate what's happened in the computing industry up to now. And so we're looking for new architectures for computing, such as what goes on in the brain, neuromorphic computing. And the diagram on the left shows our desire to reduce the energy cost per bit, to make things more complicated, but as well minimize error rates. And in order to do that, we need to again move towards that red star on the bottom of the diagram on the right-hand side But here we need to use different devices and different materials from conventional CMOS. So things like spintronic, topological and organic materials, and use, as we heard earlier on, things like chargeless computational schemes and collective switching. Final slide, please. So if we think about where we are now, we have world-class scientists and engineers in the UK and some state-of-the-art facilities. Now we can take those and we can combine them with new approaches based on big data and artificial intelligence to materials discovery. We can look to add in piloting of new materials all the way through from fundamental research to wafer scale fabrication and manufacture. And then look at the real importance of materials recycling, testing and metrology. If we can put all that together in the UK, then we can deliver a transformative program to deliver on society's increasing energy demands, but reducing its carbon footprint. We can attract industrial investment into the UK and capitalize on our real strengths in advanced materials. And importantly, we can enable the UK to be the internationally leading innovator in the device supply chain for electronic devices and provide that sovereign capability for the UK. Thank you very much.
Thank you very much, Edmund, and indeed all of our speakers in this session. So prior to the question and answer session, just going to summarize some of the key findings again. Next slide, please. So these were findings which were common across all the topics which were looked into. The first of these is the need for infrastructure to transfer technology from lab to prototype devices. Secondly, the need for national facilities for device metrology and degradation testing. National coordination of industrial and academic research programs with targeted investment from UKRI and elsewhere to unleash potential. To legislate the uptake and implementation of low carbon technologies, that research materials should be resource abundant, scalable and recyclable. And of course that we have the people needed in the UK to deliver this. That's training programs, PhDs, PRAs and support from researchers and industry as well. Next slide, please. Now, if we are able to get all these things lined up, then the impact of the UK is, of course, significant. We will meet our 2050 net zero target. We will create new jobs and fill skills gaps and help rebuild our economy as we emerge out of the current situation. And also we will provide, as Edmund just stated, energy security for the UK for the foreseeable future. Next slide, please. So just a final reminder to send your questions in. We already have some, so if we don't get through all questions in this session, we will answer them and post them following the event for delegates to read. So next slide, please. And can we also turn on the cameras of our speakers in the previous session? Thank you very much. So here I have the pleasure of presenting questions to them, which I have not seen before, so please bear with them, with their answers. So first of all, I'm going to ask Dr. Robert Hoy. So question for you, what is the expected capacity factor for future photovoltaics installation in the UK? And aren't they substantially lower than onshore and offshore wind?
So first of all, for the capacity factor, we heard earlier today from Professor Orford that UK's capacity for photovoltaics is 100 times greater than what we have right now. So there's huge potential for further development. In terms of so just based on that, I mean, that can go a long way towards delivering the extra energy needs that we require for renewable energy supply in the UK. And a lot of companies have looked into this into quite a lot of detail, and they predict that it's very much feasible that by 2030 we could have photovoltaics providing 50% of the renewable energy needs of the electricity that's supplied in the UK.
Okay, thank you, Rob. So I've got a question here for Javier. So I mean, what is the conversion efficiency for caloric devices? And perhaps I'll add to that, what's the potential for them?
Thank you very much. So at the moment, the conversion potential of the materials itself is very, very high, and is very close to the maximum theoretical limit that allows thermodynamics. So that means that if we can develop heat pumps based on caloric materials, we could really achieve much higher energies and save a lot of energy that we dedicate to heating and cooling. But we still need to do quite a lot of work on the prototyping side of things, because we have very promising calculations on materials performance, where we need to build prototypes and test the real energy efficiency, which is something that many groups, both around the world and in the UK, are starting to do. And I envision that this is going to be very important work to do in the next few years.
Okay, thank you. Okay. Keep going. Yep, keep going.
I was in terms of the potential, we are already using heat pumps in many homes, but these are based on vapor compression cycles. The efficiency of the current heat pumps is not bad, but it could be improved because of the nature of the fluid cycle that we exploit. So with solid materials, with caloric materials, we have the potential of both increasing the energy efficiency of the heat pumps, but also basically obviate the need of using a gas. So if we use a solid, we are not going to contaminate the atmosphere with the refrigerant. So in a way, it's a two-fold win situation.
Okay, thank you, Javier. So I'm going to address the next question to Ivan. Ivan, this question is, how long do you think we are away from identifying a killer economically viable catalyst for CO2 reduction?
Well, actually, there's been a huge, that's a very good question. There's been a huge amount of progress very, very recently, actually. We're going from kind of order of milliamps per centimeter squared to amps, actually. Now, because we're starting to use geometries more similar to electrolyzers. So there are already actually commercial CO2 reduction electrolyzers, for example, from a Danish company called Topso, but they're operating more niche markets. But obviously, what we'd really like to do is to make a chemical like ethylene, which is now one of the most widely used chemicals. I think it's still a few years off, but certainly on a prototype level, there's been a huge amount of advances already. It's difficult to give a very exact time frame.
Okay, thank you very much. So the next question is for Professor Linfield. Does the UK have sufficient semiconductor industry to be able to sustain beyond CMOS research?
That's a good question. I think it does have the industry to be able to sustain it. I think there's a lot of industry that can support the innovation pipeline through that. Where we come to manufacture, that's another question we need to think about. But I think we can look at that pipeline, and I think we've got the industry that can support and drive it. And we saw that through the workshops with a number of industrial partners in the UK that actually showed a real interest in the areas we were looking at. So the answer to your question in brief is I think we do, but there's a lot of work to do to actually bring more industry in and to link that industry with academia across the UK.
Okay, thank you. And staying with you, Professor Linfield, so in terms of the combination of functionalities of CMOS and others, such as piezoelectrics, can you clarify, did you mean that we need to develop new materials that can perform, for example, as a better transistor or piezoelectric device at the same time, or is it just integrating functional devices on CMOS wafer substrates?
In this particular instance, I think we were really thinking about integrating existing substances with this into a CMOS substrate, so you could combine functionalities in a single chip, and that was the primary thing we were thinking about in this particular roadmap. Of course, there may be new materials that would be good to integrate with CMOS, particularly going forwards, and some of the longer term solutions may be about combining CMOS with the new technologies we talked about in terms of this neuromorphic computing and the new types of transistor. But in the first instance, it was combining existing materials with CMOS to make compact, efficient devices, rather than having to separate those out.
Okay, thank you. So next question is to Dr. Fenwick. So Oliver, what contributions to the net zero goals is projected is a projection that thermoelectrics can make?
Yes, this is a good question because, of course, thermoelectric technology is deployed at the moment, but actually on a relatively small scale compared to, for example, for some of these other technologies. There are two ways that thermoelectrics can do this. One is through recycling waste heat. And that is a vast resource, but doing it efficiently is the challenge. But it is so vast that if you could even do it at a few percent, recycle a few percent of that, it is a significant contribution. In terms of kind of heating and cooling, you do require a much better performance from the thermoelectric devices to compete on efficiency with other materials. There's still reasons it competes, but not necessarily always on efficiency. And but this is a something. This performance of thermoelectric materials has been improving, right, quite rapidly in recent years. And I think on a roadmap that incorporates also long-term ambitions, we could see thermoelectrics picking up a lot more in that area. Okay, but in that area, I would not want to put a very fixed number on what thermoelectrics would contribute, but it can be significantly more than that.
Okay, thank you very much, Oliver. So I'm going to return back to Dr. Hoy with a question now. So some of the technologies which are discussed benefit from a clear optimization metrics. So the ZT coefficient for thermoelectrics. For PV, what is the material property that is the bottleneck that we must overcome?
So what I want to emphasize is that there's a range of materials that we're considering. Currently, in the current market, it's dominated by silicon. So that, as Professor Nelson mentioned, is 95% of the world's market. And if we look at silicon, silicon has an efficiency limit of 29%. And in the lab, after 4 decades of research, it's reached 27%. So it's very close to its theoretical limit in the lab. So in that sense, people are thinking about ways to overcome this efficiency limit. And one way that people are thinking about is to make a multi-junction device where people combine 2 different band gaps together. So the silicon absorbs near-infrared light. If you put a visible light absorbing solar cell on top, such as a metal halide perovskite, then you can get up to 43% efficiency. And realistically, the UK is a world leader in looking into this technology in perovskite silicon tandems. And realistically, it's predicted that these can deliver modules which are 35% efficient. And that's 50% larger than what can currently be achieved with silicon-based modules. So this is one really promising future area that's realistic that we can achieve.
Okay, Robert, also in relation to that materials question then, so perovskites are typically lead-based. Is there a plan to mitigate the health risks of using lead in perovskite solar cells or alternative systems we can use?
Yeah, absolutely. So there are 3 things I want to say about that. So first thing is, if we look at the lead that's in the perovskite, it's less than the amount of lead and materials that we worked with in the past. For example, people used to use lead-based paints, and the lead in the perovskite is 10 times less than that. Now, it's still important that the fact that lead is toxic, so we need to think about a life cycle analysis for a perovskite solar cell. And people are very much thinking about that. So, for example, people are thinking about ways to sequester, to scavenge the lead that may leach out from a device, such as by having a coating with phosphate ions that can pull apart the lead ions that may leach out when the perovskite device were to degrade. So just a third point I want to make is that there's a lot of research right now in thinking about how we can move away from lead. So, for example, can we move towards bismuth-based materials, which are much less toxic, but which can replicate the exceptionally good optoelectronic properties of the lead-based perovskites. So that is still in the fundamental stages of research, but it could have large long-term impact.
Thank you, Rob. So Professor Linfield, question for you. So in terms of developing national facilities for degradation testing, what sort of key degradation factors are particularly important for the applications you've mentioned, for example, monolithic integration of CMOS for reducing energy consumption. Edmund, you're muted, just to say.
Apologies. So I think that the really important thing, and perhaps I'll just broaden it slightly from degradation, is the really important thing is we know what's going on when we look at our materials and devices in the research environment. I think it's really important as we scale up and go to the next scale that we look at how that translates going forwards, and we can look at the degradation, the materials properties, how they integrate together, and whether we actually have things working in the same way they do in an academic environment. So I think as we go through it, we need to look at degradation, of course, of all the things about how long they will operate for, the power consumptions and things like that. But more important, I think more importantly underpinning this is what we can find in our academic institutions. Can we scale this up? And what happens as you scale it up? Do we get the same performance, or does the performance change? And so I think all the aspects of the device, we need to look at what will happen over a period of time, and particularly if those devices are going to be used in remote environments where it's very difficult for them to repair. And some of the Internet of Things applications will require us to have remote devices where we need to look at their performance over a long period of time without degradation.
Yeah, and also staying with you, Edmund, a more specific question, which may come out actually in the roadmap details when it's in full. That is any work being conducted on dielectric ceramics for low loss electronics? Are
you asking specifically about the roadmaps or generally across the UK?
It's just a general question. How does it feed in, I guess, to what our thinking is in the roadmaps?
I think you will see when the roadmaps come out as they're developed, if you look at some of the areas, and particularly the third area I talked about, which was new computing architectures and new devices, what you'll see as you go through that area is a vast range of materials that people are investigating and device concepts that people are investigating. In this particular area, we're looking for what we need for 2050. And so there's a broad range of research that's happening, and we need to pick out the things which will be most critical. So the answer to your question is, these materials all underpin what we're thinking about for the future, and we need to work out which are the ones that are going to actually deliver what we will need. So I think you'll see more of this in the actual roadmaps as they come out. And if things, and there's a very specific example there, aren't in the way that you feel they ought to be in, then what we would ask is people actually come back to us and actually help us shape those roadmaps over the summer. So I think my answer is you'll see more on the roadmaps, and if it's not there, please do let us know.
Okay, thank you, Edmund. So a question for Javier. What does the roadmap, what is the roadmap really to address the carbon reduction of heating in homes looking like in terms of contrasting heat pump technology, use of calorics versus hydrogen versus energy generation from hydrogen, etc.?
Thank you very much. So I think when one looks at the different options for particularly heating of buildings and vehicles as well, there are these three alternative technologies. So we can, of course, burn a gas, and then the efficiency normally is 1. So you get as much heating as you could work. COPs, or coefficient of performance of heat pumps, are much better than boilers, let's say, because they can move energy in a more efficient way. And normally with existing heat pumps, you are looking at coefficient of performance of around between 2 and 3, which are actually much better than boilers. And this is why there is a trend to replace boilers that are inefficient by heat pumps. But then when you look at traditional heat pumps that are based on expansion and compression of gases, because of the nature of the thermodynamic cycle that you exploit between the gas phase and the liquid phase, there are some limits on the maximum efficiency that you can achieve. And this is where caloric materials can become interesting, because there are actually theoretical calculations and modeling that show that you can actually go much higher than this coefficient of performance at the moment of 2 and 3 when using a solid. But as I said before, this is very promising. This is also a very early age technology. I mean, it hasn't been around for very long. There are a number of companies in the UK pushing this technology, and breakthroughs are coming. So I think for the next years, the real test is how we can actually develop the systems as well as the materials, and then show really high efficiencies that basically can then replace existing products that are in the market.
Okay, and actually staying with you, Javier, if we can. So, Colorex, I guess, is not a well disseminated technology. So, what are the implications of moving towards these solutions in terms of physics education and what we teach and the future skilling of people?
Right. So that's a very good question. I mean, me and others actually are spending quite some time in outreach activities to basically spread this technology. It's actually been around for a long time. I mean, calorics were actually discovered in the 19th century in the UK by the teacher of Dalton, the chemist. But they haven't been really pushed into technology for many years because vapor compression is very good at what it does. I mean, it can deliver heating and cooling, and it's actually very cheap. So this is why it's been very difficult to find a motivation to replace them. But now we have the environmental reasons to replace this very old technology, which is vapor compression. And I think if you look in most thermodynamics books, actually there are some sections on how you can use solids and these caloric materials to achieve heating and cooling. So perhaps introducing or reinforcing a bit more when we are talking about thermodynamics, explaining this kind of like modern practical application of materials. So that may be a nice link to show that thermodynamics, how you can apply thermodynamics in modern applications. So that may be an option. And then also bringing these materials to university degrees as well, I mean, to the forefront and explaining how these materials can play a role in future technologies.
Thank you. Just on for Dr. Stevens. So Ivan, do you see a significant role for solar-powered chemical catalysis, e.g. hydrogen production and so-called solar fuels?
So I guess there's just two ways of looking at it, right? That you could either have a photovoltaic coupled with an electrolyzer, and I think certainly the kind of very low costs of solar energy from photovoltaics now makes that very much more attractive than it was, as long as you can get the capital costs of the electrolyzer down, for example, by decreasing the cost of catalysts and decreasing cost of electrodes materials. Another option, of course, it would maybe in the longer term would be to direct photocatalytic water splitting. That's still not quite efficient enough yet, but it has a potential for being a lot cheaper because you have a simpler system essentially. But again, you need better photoabsorbent materials which are more stable and cheaper than that currently exist.
Okay, thank you, Ivan. So we're moving towards the end of the Q&A session. I'm going in a minute just to ask each of the speakers just to give us one key message, if you like. But prior to that is one question which I guess I can take, and that is, what is the international aspect of what we've been talking about? Well, of course, the whole road mapping exercise was based upon the UK's need to reach its 2050 targets, and in some areas that will be reliant upon ourselves as a UK community moving that forwards. But clearly, in some areas of the technologies, these aren't going to be developed solely within the UK and will involve international cooperation and engagement with industry. So we have engaged with industry partners. We will continue to do so over the next few months as we refine the roadmaps. And clearly, the UK sits within, in terms of funding, a global landscape for carrying out research and also taking things to market. So it's absolutely important that we do consider the international aspects, and we will. But equally, we also have to make sure we have our own home resilience to actually addressing these topics. So I'm now going to ask each of the speakers just to wrap up. I'll go in order of their presentations. So I'll start with Dr. Hoy. Can you give us your key message, please?
Thank you, Rich. So I would say that the key message is that the UK already has a lot of talent for photovoltaic materials research. And in many cases, you can consider UK to be one of the world leaders here. But the key challenge is to take the research into industry Currently, there's no manufacturing capacity in the UK for photovoltaics. And if we don't do something about it, the new ideas and the new innovations will go overseas and the UK will lose out economically. So what the UK needs is to have dedicated funding routes to take research into industry. And we also need to have their supporting infrastructure. So that's central facilities for degradation testing and device metrology, as well as pilot production facilities to help people to go from the cell, working at the cell level to the module level.
Okay, thank you, Rob. So, Ivan, can you give us your key take-home message?
So I would agree with what Robert said. We need integration between the academia and industry. We also, I would say, with hydrogen right now, it's already pretty, we have electrolyzers that work well, but they're just not quite durable enough. They're not quite scalable enough. For example, there's too much of precious metals, iridium, for example. So we need new materials that get rid of these bottlenecks. And the UK is very well placed to do that, I would say.
Yeah. Oliver. Oliver, yeah. I think you're muted, Oliver. We can't hear you. Okay, we'll quickly jump on to Javier and then see if Oliver can sort his microphone.
So I guess my main message is that this new technology, this caloric technology, is really disruptive. I mean, it's very different from many other approaches that we have for heating and cooling. The contribution of heating and cooling to global warming is really relevant. I mean, it's really large. So this is an area that we should concentrate efforts. And I also wanted to say that we are very fortunate because in the UK, actually, we have some of the world leading groups in academia working on caloric materials. But we also have startups companies that are really pushing this technology and indeed are actually competing with the largest manufacturers of air conditioners and heat pumps in international competition. So I think this is really a crucial time for this technology. And in terms of going forward, I think we need to concentrate on discovery of materials with even better performance because there is plenty of room to find even better performing materials, improving the existing ones in order to tailor the properties to the specific applications. And equally important is also to work on the development of prototypes and systems that can really show that this technology is energy efficient and then help informing the market and introducing these new products.
Thank you, Javier. Oliver, try again.
Yes, so I hope you can hear me this time. For thermoelectrics, the market is growing at the moment. It's already growing very rapidly, and the UK is well placed. It's well placed academically, it's well placed in industry. And so I think in the short term to medium term, we can look at research and policy that accelerates this growth in the uptake of technology. But to make a significant impact on our 2050 targets, we also need a program of materials discovery and to explore these new classes of materials that are only just emerging. So I think the messages from thermoelectrics is we've got an established industry, but we are still learning about the science and the applications. To do that, of course, we need things that are common with many of these areas like people, facilities, and continuing and improved dialogue.
Thank you, Oliver. And finally, Edmund.
So I'm going to put two things just because I will. And the first one is, I think if we just go back to the beginning, the 2050 net zero target is very, very challenging and very ambitious. So for me, across all areas, what we really need to do is get the whole of the UK working together and with international partners, whether it's academia, national laboratories, or industry. And we need to have that full pipeline of research, as we've been hearing, from fundamental research all the way through to prototyping, manufacture. The other thing I think that's come clearly, and we heard this at the earlier talks today, was we really need to think about recycling of our materials and also the replacement of those materials that are scarce. And so for me, the two things are, we need to work together as a UK and internationally to address these really ambitious targets, which we must address by 2050. And we also need to look at the scarcity and replacement of some of the materials we're doing and look at recycling for electronic devices. Thank you.
Okay, thank you, Edmund. So Finally, I'd like to thank all of you again for your presentations in this session. And I'm now pleased to hand back over to Professor Neil Alford to close today's launch.
Okay, thank you very, very much indeed. I'd like to thank all of those people who asked questions, and thank you to the speakers for answering them so well. So next slide, please. Okay, so we're at the 15th of June, and we've just finished the launch of the key findings. And what we really need now is the community's involvement in refining the roadmaps. And you will receive, on Wednesday, we will be publishing the executive summaries of the roadmaps, and you will all receive those executive summaries. And we really do need your input in order to refine those particular roadmaps, because we hope to publish them in September of 2020. So next slide, please. So what happens next? So as I said, on Wednesday, actually, all participants will receive the link to the executive summaries, and the roadmaps will be available from July, and they need the refinement. And so we do need your feedback. If you're not already involved with the road mapping, but would like to be involved going forward, then do get in touch at scienceandinnovation@iop.org, or respond to the survey, which will be sent to everyone, all the participants, after this event. Next slide, please. So I'm not going to thank everyone by name, but I would thank all of you, Materials for the Energy Transition community, particularly the workshop attendees. Thank you very much. Big thanks to the plenary speakers. I'm very grateful for them giving up their time. Thanks to my colleagues on the steering group. Thanks to the road mapping leads who took that forward and did an enormous amount of work to prepare those roadmaps. And thank you to the Institute for Manufacturing for pulling that together, pulling the road mapping together. Finally, I'd like to thank the Institute of Physics and the Henry Royce Institute. And maybe I will just say a huge thanks to Izzy, Amy, Lata, and Katerina, who did a fantastic job in pulling this all together. So that's it. That's all, folks. Please do respond to the request to put input into the roadmaps. And thank you very much indeed. Goodbye.